network traffic classification. So why we are talking about network traffic classification first of all? So let me go to the next slide. Yeah. So network traffic monitoring. So we used to analyze network traffic for various tasks such as security monitoring, load balancing, resource allocation, and many more tasks. However, for any kind of network traffic monitoring or any security analysis or resource allocation, load balancing, first we have to look out for network traffic classification, as it is one of the most important prerequisite for all those tasks. So, for example, let us take an example to understand that. So if we consider the case of 2016, where Mirai attack was launched on a network. So it was a very popular attack launched by IoT devices in a network. And the DDoS attack was launched, and about 1.6 approximately or 138 billion loss happened for that attack. So considering the same scenario, if we are having a network, if we consider the same scenario like ISC, and a lot of IoT devices may be installed in the network, as well as the normal computers and PCs are also in the network. So if we get news or that, okay, Mirai is being launched, or some attacks happened in USA based on IoT devices. So in order to prevent or mitigate that thing at that time, before finding out the solution, we have to stop the network traffic of IoT devices. For that, we cannot stop the network traffic of the whole network of ISC. That is not possible. At least other devices should run in a normal way, and only the IoT network traffic or the packets of ongoing and outgoing of IoT devices must be dropped off. For that, traffic classification is important to identify in a network, means at the gateway, that okay, these packets belong to the IoT devices, and these are for non-IoT devices. So this is the one of the example of the motivation to work for network traffic classification. In literature, network traffic classification is done by two ways: shallow packet inspection and deep packet inspection based methods. So in literature, many methods fall under shallow packet inspection, and other fall in deep packet inspection based methods. Okay, so what are the challenges for network traffic classification? So growing internet users. So right now we are having like about 2 to 3 billions of end devices which are being connected with internet, and it is a challenge for any end device, and even with the upcoming industry 4.0 and all those things, where and 5G networks where lots of other devices will be connected to the internet. So it's very tough, or it's a challenging task to classify different type of devices on the gateway of any network in order to do all such security related tasks. This is one of the challenge. Another challenge is the use of number of proprietary applications and application protocols. So nowadays, industries who design products doesn't directly rely on that. Okay, we'll work on web traffic and use standard HTTP ports 80 or HTTPS 443 and so on. They use their own protocols, and many of the times they run on non-standard ports to generate any kind of network traffic belonging to that application. So use of different type of proprietary protocols again makes network traffic classification very, very challenging. Use of IoT devices along with traditional network devices. So and motivation for that I have already given by talking about Mirai and all. So in general, we can say that nowadays internet is generating very huge and heterogeneous network traffic. So if we talk in terms of any industry, or if we talk in terms of any organization or institute, so the incoming and outgoing traffic from any of these infrastructures contains variety of network traffic, not just of PCs or not just of mobile apps, but also different type of devices and IoT devices. So these are the very basic challenges to work with network traffic classification. And the earlier used methods for traffic classification doesn't work with today's scenario, and we require more uh, uh, we can say method we require all such methods which can solve all these problems which are shown here. Okay, so what are the available classifiers? So I won't go into a lot of literature. So whenever we'll come with work and then we'll talk about the literature of related to that work. So available classifiers are the text application protocols and binary application protocols. We have this different type of protocols, and the basis of that we have different type of classifiers to identify different type of application. But the issue with all such classifiers is that number one, things are not running on standard ports. So all those classifiers which are classifying on the basis of ports, like services running on 80, which are running on 443, which are running on port 21, which are running on port 23 for TCP, and for this is for HTTP, HTTPS, DNS, and all those type of application services. So it was like standard previous time, but nowadays many protocols are using ports which are having value more than 1023 or 1024. 0 to 1023 are standard ports, and after that are the non-standard ports. So this makes these port-based methods insufficient for classification. So many methods came for SPI and DPI-based methods, shallow packet inspection and deep packet inspection-based methods for classification. So shallow packet inspection, if we create a packet, so as per the TCP IP suite, we have physical layer, and then they have data link and layer and transport, which is network layer all combined, and then a transport layer and overall the application layer. So this is as per TCP IP suite. So all those classifiers which can classify, which can identify application just by analyzing anything but not the payload. So just analyzing the headers and finding out that okay, this is the application, comes under shallow packet inspection methods. The advantages of shallow packet inspection based methods are that they are fast to classify, because they don't go into very depth of the packet. They just analyze the header and try to classify the application. But the issue is that the accuracy, because when we come to deep packet inspection, it analyzes the headers as well as the payloads. So which is the actual content which is transferred between two end devices. So it gives a lot of information about what type of application is running. So this is the advantages of DPI, that they are highly accurate. Again, there are two big disadvantages of deep packet inspection based methods. First, the DPI based methods are pretty slow as compared to SPI, because they analyze the payload, the actual data which is being transferred between two devices. Another thing is that it is hindering the user's privacy. So if DPI based methods are accessing the data, so whatever is the information shared between two devices is also shared with the classifier. So it is required to design deep packet inspection based methods which are lightweight, means even if they analyze the payload, they should not be heavy methods, as well as they should hinder minimal privacy, means take a look on minimum payload to identify any kind of application. If it is possible not to look more than some 50 or 100 bytes, then it is considered as good. And if you are reading the whole payload, this means you are entering the user's privacy in total. So the requirement of classifier is that which can concurrently classify all kinds of application, whether it is a text-based protocols like HTTP and HTTPS, or Dropbox also uses a LAN synchronization protocol, And there are different binary application protocols like DNS is there, network time protocol is there, and so on. And different proprietary protocols. Apple uses its own protocol, and brother printers, which are Japan-based printers, they use their own protocols for connection. Even IoT devices uses their proprietary protocols. So a robust classifier is required, which is lightweight and can accurately identify such different type of applications concurrently simultaneously in the network. So what we does, we proposed two methods for that. We proposed BitCoding and BitProb. So this was published, I think, in 2019, and this was published in 2021, or I think 2020. So these two methods we proposed to mitigate all such issues which happened previously. So both the methods are bit level payload analysis methods. So these methods are lightweight because they analyze only few bits of the payload to analyze the network. So these methods are computationally very cheap as compared to other deep packet inspection based methods, as well as they do not hinder the user's privacy. We can, when we'll see experiments, then we can see that only first 64 bits of payload is sufficient to identify the different kinds of applications. So both the methods are supervised methods, and computationally less expensive. So yes, these are supervised methods, but none of the method is machine learning based. We have not used any kind of machine learning here. Instead, both the methods are statistical and uses different kinds of automata which we have created, which acts as application signature for classification. So we'll take a look one by one. So both methods can classify text protocols, binary protocols, and whether any of the text or binary protocol is a proprietary one or a non-proprietary protocol. So these are the two methods which we propose. So
hello.
What I had,
yeah, sorry, I had a doubt. Why we are going from SPIs to DPIs? That part I didn't understand. Like the motivation to go from SPI to DPI, because DPI you have a constraint that I want to see the minimum amount of payload. Then the minimum amount is you don't see the payload into SPI. So what is the motivation of going from SPI to DPI?
SPI methods are we can say less accurate as compared to DPI. The issue is that because it analyzes only header, and with so many devices are coming into picture, different type of text protocols, binary as well as proprietary protocols. Many times header remains very constant for, if we analyze, for example, say 50 protocols. It may happen that out of 50 protocols, 5 protocols are there which are having same header content. We cannot identify these 5 as different application protocols. In that case, we need to go for DPI-based methods.
Okay. Yeah, thanks.
Yeah. So this is the reason we moved to deep packet inspection. And so we are trying to find out the solution by using DPI, but hindering the minimum user's privacy. The reason is that it is much more accurate than SPI-based methods. So these are the two methods which we use, BitCoding and BitProb. However, BitProb solves the issues with BitCoding, but we'll go with both the methods together and see how they work and identify applications in the network traffic. So instead of going here, let's go to the process one by one. Okay, and what I have done, I have tested both the methods on same data sets. Actually, those data sets are not the old data sets. Instead, we have used the live network traffic and compared both the methods and find out that how they perform. We have also compared both of the methods with recent literature to find out that how lightweight and accurate they are. Okay. So the motivation for going at bit level instead of byte level. However, at the byte level also we can do network traffic classification by analyzing few bytes, like some 2 or 3 bytes or 4 bytes or 5 bytes of payload. But the issue is that There are many applications like network trying protocol, remote procedural call, BGMP protocol, BACnet. These are the proprietary protocols. So they use us bit level encoding. Like if we just see this network time protocol header, so it doesn't have, like in HTTP we have get, post, and put method, where we can read the data and strings and find out that where this get needs to be go and put and post. But it's like that, if this bit is 0 or 1, then what is like that? So in NTP right now we are using NTP version 4. So in 4 binary, I think can be coded as 0100. If I'm correct, I don't know. So if it is 0100, so obviously these 4 bits from bit number, if we say this is bit number 1 and this is bit number 2, 3, 4, and 5. So these bits always be 0100, which identifies that from bit number 2 to bit number 5, if you read this binary and convert into its decimal format, then it will be turned out to 4, which identifies the version of this NTP, network time protocol. So similarly with all those, there are different type of modes. So strand term, and whether it is a polling, how much precision on the time is there. So all those kinds of information is being done in 32 bits, and each bit with its position has its significant meaning, and this cannot be done with byte level methods. Therefore, we also move to bit level methods, that okay, we can classify different kinds of protocols, whether it is byte level based or bit level based, via bit level classifier only. So among the methods in literature which uses these bit level methods can classify either only binary protocol, or they parse payload up to 1024 to 8192 bits, or 1024 bytes. So this is a very big data chunk to be read. If they read so much data, then again the user privacy is hindered. So we require a very computationally cheap method. So these methods are computationally expensive, and for that, let's see how BitCoding works one by one. Okay, so this is the architecture of how the first method BitCoding works. So first we take the network packets. So either it can be a real-time stream of network packets, or it can be the packets which are stored as a PCAP file, packet capture format. Then bidirectional flow is constructed from packets. So bidirectional flows can be TCP flow or a UDP flow. So TCP flows are all those flows. So if there are two entities, entity A and entity B, and if they used to talk, and so how it happens, TCP three-way handshake happens via TCP SYN, SYNAC, and ACK. And after that, whatever information they want to share, they chat, and from FIN, TCP FIN, they close the connection, and then acknowledgement is received. So all those packets from this to this, including all the data packets in between, when combined together, makes a TCP flow. So this is how TCP flows are constructed, and other are the UDP flows. So usually what happens, most of the applications runs TCP or UDP only as a transport.
Sorry, Mayank, can I ask a question?
Yeah.
So I'm not completely following this. So you have network packets.
Yeah.
From this, how do you do this bi-directional flow reconstruction and n bits instruction? So first of all, do you know this n, or it depends on the protocol to protocol? Does it change?
No. This n we give as input. So how much bit signature we want to extract? It depends. So if I'm an administrator of our network, so I give the value of n, that okay, for this value of n, maybe I'll get a good network signature. I test on a small set, and then I'll really implement it on a network.
So you're saying that, so in the reality, you would change this n from time to time, like depending on different experiments, you'll have different n? Is that?
Yes, obviously. So this n varies. It depends on what kind of organization it is and how data is flowing in that network. because it's a very dynamic.
So fair. And the second thing is that what is this bidirectional flow reconstruction? What do you mean by that?
Bidirectional flow, I just explained that all those packets between a TCP connection and TCP disconnection, it makes a TCP flow. So we reconstructed the whole TCP flow, and then we extracted only first n bits out of it.
No, I don't understand. So in the network, a lot of TCP flows are going, right?
Yes.
And every flow would have many packets, right? So
yes.
So what is your suggestion here? Like sample every packet or some packets of this flow, or I mean, I don't understand what is the suggestion.
Okay. I'll make it easier. I'll make it very easier. So how it works? So if I have a PCAP file may contain, say, 1,000 packets. So
sorry. So okay. One second. So are you saying you're doing this post facto, or you're doing it online? This algorithm which you have.
So this we have tested on PCAP files, stored network traces.
I see. So you're not doing this on running network. This classification. This is.
You have training. For training, we need to keep it on offline. Once the signatures are generated, it can be tested on.
Okay, got it. So now please go ahead and explain. So for training, go ahead.
Okay. So I think you got it now. Till this point.
Yes, please.
Okay. So if we have 1,000 packets, maybe some 100 packets make flow 1, another 100 packets make flow 2, another 50 packets makes flow 3. And another 70 packets makes flow 4. I'm not saying all packets should be in sequential that only. It can be a mixture, but we can identify this bidirectional flow using various concepts. But we have used an inbuilt library known as JNet PCAP flow. It's a Java library which fairly with 100% accuracy. It's a standard library which extracts different flows from PCAP files. So we have extracted these kinds of PCAP, and then we have generated signature. And how we have generated signature, I'll show you from these flows. And based on this signature generated, once it is generated, we have implemented run length encoding. Why we have put it? Because this makes signature size smaller than the normal. Even if it is a 64-bit signature, we can compress it so that it can run in a faster way as if we keep it like raw.
So can I ask one more follow-up question?
Yes.
So you generated these packets, right? So you know pretty much the ground truth, like how you're generating them.
Yes.
Or is it from a data set you downloaded from somewhere?
So we have 3 data sets, 2 which are publicly available, and 1 we have generated in our own lab.
Okay, thank you.
Yeah, and for ground truth, we have all information about what type of protocols are there to generate application signature. And obviously it's a supervised. So obviously when we pass the application A1 in this network packets and to construct the flow, the application signature for A1 is only created.
So also what is the bit signature generation? I mean, is that the 2 methods you said that BitProb and...
Yes. So this will generate bit signature for BitCoding method.
Okay.
So let's go to the practicality. Instead of just seeing this diagram, it will be...
One question. In your formulation, when you say flow, is defined by the 5 tuple, right?
Yes.
5 tuple fields.
Yes.
Okay. Thanks.
So so 5 tuples: source IP, destination IP, source port, destination port, and L4 protocol. Okay. So how
one question?
Yeah.
Sorry. So here, when you say n bits extraction, that is from the flow, right? Not packet wise.
Yes, flow. Once the flow is reconstructed, we extracted first n bits from the flow.
Okay. And in the bit signature, do you have a threshold for the signature, size of signature? Is it defined by you?
Yeah, it's n.
The bit signature is n, and n will be varying as per what the flow is and what the app is.
No, n will vary for the whole experiment. Means for the if for an organization, if I'm an architect, security architect of IIT BHU, I decide the n. So all application will have signature of n bits only. It's not like application A1 is of n bits, application A2 will be of m bits. No, all application signature will be exactly of n bits, so that a match or a mismatch can be done fairly by matching those n bits.
Got it, sir. Thank you.
Okay, so how this signature is generated? So when we extract the first n bits of, say this is application A1, for we know that we have this is a supervised method. So if it is an application A1 and different flows, for example, we just took 3 flows belongs to application A1. Then, and these are the n bits which are extracted. So for this example, we can count how is this n. So this is 20 bits, I think. So if we see the unvarying bits, so all those bits which are remaining unvaried are kept same value in the signature, like all ones are found in all bits. But all those bits which are varying, we have kept as star. So this becomes the signature for application A1. And how it will help? So for example, if it is an NTP, network time protocol always runs version 4. So obviously these 4 bits for NTP will always be 0100, even in the signature. So similarly, with all kinds of protocols, we construct signature like this. This is just an example to show. Now we make a run length encoding for this signature because this is 64 bits, 20 bits. We can reduce it like 8W6Z 3 star and 3 ones. So we compress this information so that when we design the automata, we design the automata based on this run length encoding. So this is how we compress any signature. So for any application we pass, if we pass 50 applications, so 50 application signatures are generated, and each application signature is of n bits. Pretty simple method.
One question,
okay.
In this encoding, you define which bits are of significance, right? Or is it automatically done by the?
It's automatically done. All bits which are not changing the value, like at bits at position 1, position 0, B0, all B0 bits are 1 in all application flows. Therefore, the signature bit, the first signature bit for that application is always 1. Similarly, we check this B1. All bits.
If there are some bits which are changing but not significant, for example, if there is a checksum or a timestamp, those will also be considered as significant or of interest, right? Which actually is not adding anything.
Yeah, checksum and all are not included because this is payload.
Yeah, but even in the header, suppose there is some information which is completely irrelevant. Say, for example, if it has some timestamp or some information about, say, security payload, which is not of your interest. So those will also get counted as a classifier, classifying inputs, whereas you are not interested in that.
No, not interested in that. We are only interested in payload, application payload.
So how practical is it to have the varying, like keep this constraint of only the bits which are not varying are irrelevant and rest of it is relevant?
I didn't got your question. Can you just ask me again?
So you may have some junk data in the header itself, like first, say, 64 bits. There may be some junk information that you don't want to consider for classification. One of the examples is you may have a timestamp which is irrelevant for your analysis in the headers in the first 64 bits. So
no, if you are talking about headers we are not considering. These all information from bit B0 to Bn are the payload. This is the first bit of application payload.
Right. So suppose you have in the application payload, you have some application timestamp, which is irrelevant. First 6 bits is some timestamp, which you want to exclude in from your classification. But those bits are not constant. So in your algorithm, you will be taking those as something,
we are taking
as a
that.
classifier.
Yes, we'll take those bits. If these bits are irrelevant and they are changing the value, then they will have star at that position because they are not constant. Even they are of no use, we'll consider that in first those bits. And the same thing which you said happens in DNS. We find, if we say 64-bit signature, among some 25 initial bits are star only. But still we consider it and we can classify it.
Okay, so isn't this wasteful in terms of your effort to use information that is irrelevant?
But how will, if we keep like, we cannot vary this n, otherwise it cannot be a signature. Signature must be constant for all application. If I'll keep like, I'll take some other n bits for some application, some other n bits for other application, then during classification, how I'll find out in practicality that for which test flow, which n number of bits we need to take.
Okay, so there's no way to train the your logic for relevance and some bit of useful information.
Yes, that can be done as a future work, but if we make classifier like that, if we want to decide that, okay, these n bits we need to take, or if we want to take these m bits, this decision time is very slow if we consider real-time network. We have GBPS link, where millions of packets coming and going at a faster rate. This classifier will not work if it takes time to identify that, okay, this n we need to set for this flow and this n we need to set for that flow. It should be quick enough to work on real-time network. Therefore, we need to make it robust only. Whether we can compromise that, okay, initial 20 bits are star, let it be. But still, it will be fast enough to classify.
Thanks.
Okay.
Yeah, Sir Mayank, Samir here. I had quick couple of questions. So when you say the payload, that includes the application layer header. That's what. Like when
yes, it includes application layer header.
Okay, and do you all consider just the unencrypted, or the encrypted content also be? Doesn't matter.
Doesn't matter. Maybe it is encrypted and unencrypted, doesn't matter.
Okay, so you have tried, like you were mentioning about NTP, so I was referring NTP.
Yes. In dataset, we have all kinds of protocols. So on when I show the applications, we will have different variety of application, and let's see how this BitCoding works on all kind of data.
Okay, sounds good. And the second one, what in the example that you have, but you do the run length encoding. I'm wondering, like, how you were able to get the compression ratio, like, or is it just an example that you have, or?
Yeah. This is just an example. Like this signature.
8W6Z and content. I suppose, like you say, it's taking 8 bits here as opposed to
8 ones. So well, 1, 2, 3, 4, 5, 6, 7, 8 continuous ones in signature. Then 6 zeros. 1, 2, 3, 4, 5, 6 zeros.
Yeah.
Then 3 stars and so on.
Right, but this is on a bit level, right? So when you encode this run length encoding information itself, to take a lot more bits to write 8 ones.
Yes.
So that's where you had 8 by 20 and saying compression length ratio of 0.4.
Yes, this is just theoretically we have said. So when we'll implement, actually what we'll do, we directly don't match with this. We create an automata, kind of automata. And this next slide is only. And this run length encoding is good to make that automata.
Understood.
Therefore, we have used that.
Okay. Thank you.
So if we just take this example only, and if we remember 8W6Z, 3 star 3W, the automata created for this example is like this. So it's a simple, very simple automata we have made. Transition counting control automata. So it starts from here. So when a new a test flow comes, and it reaches the final state, then we consider that that test flow belongs to this application, say A1. So if 8W, so it will remain on state Q0 until 0 is between 0 and 8. Okay, and as soon the count becomes 8, moves to the new state. So 8 Ws are processed, then 6 zeros are processed like that. If it is between, if all zeros are coming and counter remains between 0 to 6, then increment the counter by 1. So until what value you have to increment? Till 6. So 6 Z's. And when it reaches the 6 Z's, move to the next state. Okay. Now the thing is that when you move to the next state, we have 3 stars. Okay. Star means the bits when in application signature are should not be considered. Whether it is 0 or it is 1, doesn't matter. Move it. Means move in a further direction. Either it is 1 or it is 0. If it is between 0 and 3, means 3 bits you have to process without worry. After that, if 1 is coming, then go to this state. And then when the final one is reached with the counter S2, so you reach the final state and the application, test application will come in. This belongs to this application. So this is how TCCA works. So this is just an example to show. So this TCCAs for different application protocol can be made. In the manuscript, it is there. Okay. So the issue with this method is that we find out that we measure the robustness of signature. Okay. So there are maybe different signatures. Say we have 50 application signature. But there may be signature which have a high overlapping. If there is high overlapping, that means application of, if we have application 1 and application 2, okay, take this example only. If we have signature 1 and signature 2, and it has high overlapping, then it may happen that application which belong to bit signature 1 can match to bit signature 2. Or application that belongs to bit signature 2 can map as bit signature 1. And when it happens, when the application signature has lot more number of stars. More number of stars, this means bits are very much varying and cannot be classified in different applications. So what we does for 20 applications, if we are matching, we find the relative Hamming distances between, relaxed Hamming distances between a set of application. And if relaxed Hamming distance is less, this means the application is fine, otherwise not. So this is just a way to find out that, okay, if it's very near, means a lot of stars are there in application signature, this means it's not a good signature to match. We have to increase the value of n. For example, if we keep n as 32 bits and we are getting relaxed Hamming distances like the signature with lot of stars, this means that application is a very dangerous application signature, and other application can be classified in this application because these bits are bits which we do not consider in classifier. Don't worry bits. So more don't worry bits means bad signature. So in this way, we any administrator or any architect increases the value of n for any architecture. Okay. So this is how a signature is created in BitCoding. Now, this star bits are having issues in this method. This is the real issue with this BitCoding, and this we solved in BitProb. That how this star bits and all. So how it works? Let us see. So most of the working remains same, like network packets, bidirectional flows, reconstruction. The difference comes in bit signature generation. How signature generation happens, let us see. So we take the same example. So here what is happening, instead of considering the invariant bits, that okay, if 1 is coming at this place, in BitCoding what we does, we keep this bit signature as 1. But here in BitProb, what we does, we keep the probability of happening 1 at first position as 1. The probability of happening 0 at first position is 0. So in case of varying bits, so here if we say this this last fourth bit, so the probability is 1 by 3. We have tested on 3 flows, and among 3 flows, in one flow 1 is coming. So this is the occurrence probability of 1, and this is the occurrence probability of 0, obviously, or we can say 1 minus p1 is the occurrence probability of 0. This means if we test for 1000 application flows belong to some application, so we can say that this is, with this probability, there is a chance of happening 1 here, and there is a chance of happening 0 here. Okay, so this is just a part. This is not a signature yet. This is just the probability of happening something at that position. Now we want to identify that whether it can be classified with some application signature A or not. And how we do it? We do it via probabilistic automata. So this is a simple probabilistic automata. So for first 4 bits I have made, because otherwise it will go out of the slides, or I have to make it very small diagram. So if we consider as first 4 bits, so probability of happening 1 is 1, here 1, here 0, and here both 0 and 1. So if we say, if we see in this figure, then if it bit is coming as 1 in a test flow, then for this signature move to this state. If it is not 1, if the first bit is 0, then obviously this automata will remain stuck and it will never classify in this class. So in bit coding, what it is happening, it can move to a forward state, but in BitProb, it will stuck if 0 comes here. So for first bit, second bit, 1, 1 should happen, 1 and 1 should happen. For third bit, 0 must happen with probability 1. But when we go for the fourth bit, both can happen with probability 0.34 and 0.66. So what we does, how this BitProb identifies an application. So first we created, so what we does for application A, some flows F1 to say, we say F10, we used to generate this prune state transition diagram. Then we use some flows F11 to F15 to decide a threshold value. We use the application of these flows only. So suppose if we use 1, 1, 1, 0. So obviously this is an application flow of this application only. So what will happen? We decided a threshold as when first one comes, the probability remains 1. When second one comes, the probability of happening 1 is 1. So multiply it. When 0 comes, 0 is if it is 1, then it cannot be classified because 1 has probability 0. So obviously, so this cannot be, I took the wrong example here. It should be 1, 1, 0, 0 or 1, 1, 0, 1. So if it is 0 happening, then threshold is again 1. And if it is 0, then it is multiplied by 3, 4. So for F11, the value may come as 0.34. For F12 application may come as 0.66. For F13, it comes as 0.66. Or say F14, it comes as 0.66. For example, I'm just taking an example. Then we took the average of this value and added the standard deviation. And this threshold value is kept as the threshold to identify this application A when it reaches the final state. If it doesn't reaches the final state, then it is not, obviously it is not classified. A test flow is not classified. But if it reaches the final state, it should be within the threshold. So this is how we overcome the problem of star, which happens in BitCoding, in BitProb. Okay, now let's go to experiments. So we have run experiments on BitCoding and BitProb. We have shown results simultaneously. So what dataset we took? We generated one dataset in our lab and two publicly available datasets we have taken from Digital Corpora and Netisec websites. So in the dataset which we generated are having 7 protocols, in which 3 are the binary protocols like BitTorrent, DNS, and SSH, whereas text-based protocols are Dropbox, HTTP, SIP, and SMTP. The P means the proprietary protocol. So Dropbox protocol belongs to Dropbox. When in public dataset 1, we have BACnet, BGNP, BootP, CUPS, DNS, NBNS, NTP, and Quick protocol as the binary protocols. And Dropbox, HTTP, NWBP, Microsoft Windows, I don't remember the name actually. And then simple mail transfer protocol as text. And similarly with the third dataset. Now, we performed the experiment using GNet recap library with Java. So this library is very good to extract flow-based information like flow payload and all. And we have written the whole code in Java. Then to test that both the methods are robust, we performed 3 types of experiment. First is the homogeneous experiment. That means we just took one data set, generated application signature from that data set, and then tested on in the same data set. Like if we say private data set, we divided into 50-50. From first 50, we have generated signatures, and from the next 50, we have tested the application. In heterogeneous, what we does, we generated data set from one side and then tested on other side. So we just want to identify that whether our signatures are robust enough to be site independent or not. So if we can train it on one, like for example, we can train DNS from our private data set and test on the DNS of public one, whether it is able to classify correctly or not. And similarly with like that. And then we construct and then we perform the grand experiment by mixing the DNS of different sites, by mixing NTPs of different sites, and then generating signature. And then testing on the common data set. To find out which signature is better, whether we should keep a site dependent signature to in the data to classify, or we should collect data sets from different sites and then generate the robust signature. So we perform these 3 types of experiments to identify all those things. So these are the bit coding signature for all those applications which is generated. So all this I have shown in the form of relative Hamming distance, and this is the time taken by our code to generate the signature in seconds. So we can see that like I just told that DNS, it has 17 stars initially. So there is a big chance that many applications will be misclassified. But if we say like SSH, initially 64 bits, we have no stars here. So if it is a test application of SSH comes, then there is a very high chance that it will classify in SSH itself, because there is no do not consider bit. Similarly, issues happens with Quick. So in Quick, last 16 bits are star, are the variant bits. So this was the issue with bit coding. So let's see creating the same signatures and some threshold values for BitProb for same data set. So this is for BitProb. So these are the threshold values decided for each application for each PCDA. But we can see that time taken to generate this PCDA is higher than that of BitCoding. So this is just a trade-off that if training is easier, then maybe results are not so much good. But BitProb, it takes much higher time. Like it took 275 seconds for generating signatures of HTTP, whereas here it took just 46 seconds to create a signature for BitCoding. So this is how we compared BitCoding and BitProb. So let's see the results. So this is our first dataset, private dataset, and we check the recall. So BitCoding was classified as BitCoding. All test BitCoding are classified correctly in both. DNS, obviously, we got better result in BitProb. Actually, it's looking very near about like 0.69 and 0.97. But the flows which we took, I think like more than 40-50,000 flows were there. So about like 500-600 flows were misclassified in DNS and 100, 150 only in BitProb. So we can see that in all the data set, like in private, these are the homogeneous experiment. Then that means trained from the same environment and tested in the same environment. So we found that this data set, BitProb works better than BitCoding, except for some example like BJNP. So here BitCoding works better than BitProb because this threshold which is decided for BitProb was not accurate. So otherwise what we have to do, we have to increase the signature length. In that case, we have to increase the signature length of all other protocols. And this method's signature generation and classification will become slower. So we kept it like 64 bits only and let it suffer from some misclassification. At least only if we are getting for one protocol. Otherwise, BitProb is performing better than BitCoding. Then we perform for heterogeneous experiments. Obviously, the common protocols available in both the dataset can only be compared. And we found that BitProb worked very good with cross-site testing. It's 100% on dataset 1 and 97 and 100 for dataset 2. And yeah, so this is again the experiments. So we have 3 datasets tested on 1, training on 2nd. So this is how we trained with our dataset and tested on both the public dataset. And here we trained with public first dataset and tested with private, means our dataset, and public 2 dataset. And the third experiment trained with public 2 dataset and tested with our dataset and public 1. So we tried all permutation and combination to check that okay, things are working fine or not. And more or less we are getting recall more than 95%. Again, here we are in boot P, we got 90% only because yeah, maybe in boot P we see the signature. Yeah, so we have 9 stars in the end, which may have created some issue. Continuous 9 stars.
One question: the output of your classifier is just the protocol that it is running, or is there some other information it supply outputs?
No, we have just found out that if we pass this class of dataset during testing, then in which class it gets classified. We know the ground truth. Then on the basis of that, we keep it like that. Like if we pass the 50 flows of BitTorrent and by the signature, all 50s are classified as BitCoding, then we keep it as recall 100. If it is 49, then it's 49 by 50 is the recall. Like that we have tested.
Right, but when you apply the same classifier in practice after the training, then the output that is given is what protocol it is, right? Or
yes.
Okay.
Yes, what protocol it is. Okay. So then we have all these 3. Okay. So grind experiment, I'm not showing the data. So this diagram will become much higher, bigger. Sorry. Then we compared our work with one of the recent method, BitFlow. BitFlow, what this method does, it extracts these first n bits and directly pass into machine learning classifiers. Okay, in this BitFlow. And in ACAS, what it does, it is just a byte level. So we compared with 2 classifiers. One is bit level classifier and one is byte level classifier. So this figure is compared with ACAS. So obviously, bit level method works better than the byte level method. So our method shown the good result. But when we compared with BitFlow, few of the BitFlow classifiers are better than BitCoding. So like backnet protocol, our BitCoding performed lesser than this BitFlow, but BitProb work actually very similar as BitFlow. This machine learning classifier. So this is how we compared. For many of the data sets, it performed bad when we perform this cross-site testing. So trained from one site and tested from another site, that BitFlow performed bad. Otherwise, it's fine. But BitProb actually performed better than both BitCoding and BitFlow. So these are the 2 work. And Okay, so the limitation is of the method is obviously these are the supervised methods. So future implementation is we can implement it on hardware, and IoT network traffic classification is another method. But this is really challenging because in that case we need to go unsupervised. The problem is that in today's network, when we consider IoTs, the network is very dynamic. Sometimes some IoT devices are plugged in, sometimes they are plugged out, some are installed, uninstalled. So the network becomes very dynamic in nature. And if you supervise some IoT device and it is just removed by one day and never been used, then there is no use of putting signature for that in the database and matching the test flow every time with it. So that is a future work, and in the lab we are already working towards it. And thank you, and these are the references. And thank you from my side.
Any questions?
Yeah, one question. So for testing, did you try running the learn models classifier on, say, virtualized classifier on the real traffic?
No, we haven't used that. Other methods are using a lot of machine learning on big level methods. So we are not going into it.
And so, any numbers on how long it took or like some kind of trends on the size of the data set of or the number of packets to train this data set? So
yes. Actually, I didn't put I didn't put in the slides, but in paper it's already there that we have properly divided that how much number of packets and number of flows are there in training, and number of packets and number of flows are there in testing. So the proper number have been given that. So if we add all this data set, it will come out to 3.4 million packets.
Okay. So but any thoughts on if you have to implement it in hardware, like how much time budget will you need to allocate for classifying in real time?
Budget, actually, I don't know. I'm actually not classifying on hardware. This I have kept it open, maybe for afterwards. I have just switched to this IoT traffic classification using unsupervised one, so that we can use same bit level information and try to classify IoT. But yeah, that can be implemented on hardware. I haven't thought of it right now, but this is just a direction for that.
Okay, thanks.
Yeah. So what I did, I just switched on the second future work instead of the first one.
Thank you, Professor Mayank, for an informative talk. If no more questions, we can end the session here today. As discussed before, we'd like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have been already pasted in the chat box. Thank you and have a great evening.
Okay, thank you.